All right, why don't we go ahead and get started? Again, my name is Eric Jebsen. I'm the current chair of the Chicago section of ANS. I'd like to welcome everyone to our March presentation. Very timely topic tonight, and something that's really on basically the cutting edge of everything that supports the future of the industry here with this high assay fuel. So without further ado, I'd like to introduce our speaker, Dr. Amanda Bachmann. Dr. Bachmann is a postdoctoral researcher in the Reactor and Fuel Cycle Analysis Group at Argonne National Laboratory. Her work focuses on modeling, simulation, and software development for the nuclear fuel cycle analysis. And in previous work, her previous work also includes modeling and simulation for nonproliferation safeguards applications. She holds a PhD in nuclear plasma radiological engineering from University of Illinois at Urbana-Champaign, and a master's and bachelor's in nuclear engineering from the University of Tennessee in Knoxville. And she adds in her free time, she enjoys crocheting, gymnastics, and playing with her rabbit, little R. And if she's comfortable sharing, maybe at the end, she'll tell us what the R stands for in little R. So with that, just want to mention that for the registrants, the slides and the recording will be posted. So if you missed something or you want to catch up, and a link will be sent to the Dr. Bachmann's dissertation. So for the constraints of time, she can't go through all the details. And then we'll take questions as we go along. We'll pause every little while for questions. And with that, Dr. Bachmann, if you want to take it away.
Great, thanks, Eric. Yes, let me share my screen real quick. Should be this one.
Yeah, we can see it.
Just in full screen mode here. Okay, so good?
Yeah,
okay.
Looks good.
Perfect. Yeah, so thank you all so much for having me. So a couple of notes, as Eric mentioned, probably won't get through all of these slides. The entire defense was about an hour for giving the presentation. I want to make sure we still have plenty of time for Q&A, so please, as we go through, put your questions and comments into that Q&A section. We'll try to get to them as we go through. If you're curious on some more details or interested in some of the parts that I skip over, I think we're going to get a link to my dissertation into the chat so y'all can view that at your leisure. So today I am presenting my work on the investigation of impacts of deploying reactors fueled by high-assay low enriched uranium. This was my final dissertation defense back in November, so pretty recent that I gave it. Hopefully this time it's a little less stressful. And I also do just want to mention, so, any opinions that are presented during this talk are my personal opinions and do not reflect opinions of the University of Illinois, Argonne National Lab, Chicago Argonne LLC, or the Department of Energy. So making that clear. So providing some background for my talk. So right now, a big thing that the U.S. has been looking at over the last couple of years and still somewhat to this day is how we can develop supplies of HALEU. So right now, the definition of HALEU that I'm using is the 5 to 20% weight fraction. Sometimes you'll hear LEU plus thrown out there, which is sometimes that 5 to 10% range. So I used a 5 to 20% range for this work just because that's what we don't currently have domestic or commercial supply chains for. And right now, we really want to develop these supply chains of HALEU because a lot of the new reactor designs that are coming out are looking to use this enrichment level for their fuel. And they want to use this because they can get longer cycle times, increased capacity factors, higher burnups, and really just trying to get better economics out of their reactors compared with using that the 0.7 to 5% that we typically use for current fleet of light water reactors. And like I said, right now we don't really have commercial supplies. The center's facility in Ohio, I think like a week before my defense, got their facility up and running, but still working on fully getting that scaled up. And then it's also still limited in how much of this HALEU they can provide. So we're still looking at how we can bolster this commercial supply chain for HALEU. And when we talk about HALEU production, there's two ways we can do that. There is the enrichment of natural uranium, which is what we currently use to fuel our fleet of light water reactors, or we can do recovery and downblending of HEU, so highly enriched uranium. So going from above 20% down to less than 20% to whatever we need for our reactors. Taking a step back, looking at the nuclear fuel cycle as a whole. So there's a lot of different steps that go into it. So there's the mining, which is just getting it out of the earth in some way. Milling, which is getting the uranium out of the ore. Conversion, which is taking that U3O8, putting it into UF6 form that we need then for the enrichment step. The enrichment step is where we change that abundance of the U235 compared to the U238. Then we put that into fuel fabrication. So for our light water reactors, that looks like getting it into those ceramic UO2 fuel pellets. For other reactor designs, that might look different. And then, excuse me, fuel goes into our reactor. And then once it comes out, currently what we do is we put it into storage for some amount of time. And then ultimately the goal is to put it into a repository for final disposal. And you'll notice that even though we call this a cycle, this exact configuration isn't very cyclical. That's because it's what we refer to as a once-through fuel cycle. So the fuel goes through the reactor for one session or a couple of batches, but as soon as it's discharged from the reactor, it really just goes for disposal and we don't reuse it in any way. What we can do is we can add in a reprocessing step here. So after fuel comes out of the reactor, it cools for a certain amount of time. We can separate out some of the material that is still useful for reactors, such as uranium or plutonium, put that material back into our fuel fabrication, and then the other materials that aren't as useful can go into a repository for storage. So we add, or excuse me, for disposal. So when we add in this reprocessing step, we do what's called closing the fuel cycle. So now it becomes more cyclical in how we process the materials. And then when I talked about the recovery and downblending step of HEU in order to produce our HALEU, that would fit in right here for a fuel cycle. It's already above the natural enrichment. It's already above the enrichment level that we need. So we need to downblend it with some natural uranium or even depleted uranium tails. And then it can go into fuel fabrication and then through the reactor and so on. So when we talk about enriching natural uranium to produce our HALEU, right? We're trying to increase that relative abundance of U235 in the fuel because it's not very abundant in natural uranium. And so when we talk about enrichment facilities, their designs are based on a couple of different parameters. One of them is the product mass, which is just how much of that enriched uranium do you need? The next is the product assay. Assay is a fancy word here for weight fraction. So what level of enrichment do you need out of your product material? And then also something called SWU, or separative work units, which is the amount of work we have to put into uranium material in order to provide that isotopic separation and change the enrichment level of it. We can relate various material flows through our enrichment facility. We have what goes from our conversion into our enrichment is what we call feed. So that's typically at our natural uranium level, so that's 0.7%. What comes out of it and goes into fuel fabrication at that product assay that we need is that product material. And then there's always the tails, which is depleted uranium, so less than that 0.7% uranium, or excuse me, U235, just goes for disposal. And we can relate these material streams as well as their assays through a couple of different equations. And a couple of things to note about this. When we relate the assays of each of these materials with the masses of the materials, we see that if we're going to increase that product assay, so going from, say, 4% up to 10% in what we need for our product assay, we're going to increase the feed material that we need. But then if, we need to increase the product mass that we need, then that's also going to increase the feed mass that we need. But if by increasing the product assay, we can decrease that product mass, it kind of becomes this balancing act as to which one has a greater change as to how much it affects the amount of feed material that we need. And we see a similar relation with that SWU capacity. So the product mass and the product assay, depending on how they move and how they change by changing the changing the reactor designs that we're fueling is going to drive the changes in that SWU capacity that we see. When we talk about downblending HEU to produce HALEU, so there's a couple of different materials inventories that we can use right now from that the Department of Energy has identified. One of them is the spent fuel from the EBR-2 reactor that's currently on Idaho, which can produce about 10 metric tons of HALEU. There's also HEU from the Savannah River site in South Carolina that can produce between 4 and 20 metric tons of HEU. But the main thing to see here is that these are pretty limited inventories that we can use for producing this HALEU. So it's maybe a great way to get us started for producing HALEU for demonstration or initial reactors, but it's not necessarily a long-term solution. So in some way, we're going to have to develop this enrichment supply chain for producing HALEU. It's also important to note, and this is a part I won't quite get to in this talk, some of the fuel will have impurities when we downblend the HEU. Typically, they're going to have larger concentrations of uranium-232, which is going to have some pretty nasty gamma doses, as well as uranium-236, which is a fairly parasitic neutron absorber for your fuel. So, when we talk about using these downblended HEU inventories, it's kind of interesting to look at how the uranium impurities that are present will impact the performance of these advanced reactors. And as I mentioned at the beginning, this is something that the US has really been interested in for a while now. So I'm not the only one that's been looking into this problem. NEI, the Nuclear Energy Institute, did survey multiple reactor design companies trying to estimate HALEU needs between now and 2035. I think they started this back in like 2018, writing a couple of letters to the Secretary of Energy saying, this is what these advanced reactor design companies are predicting as their needs as they go through design processes and then trying to commercialize and deploy their technologies. There's also been some efforts by the national labs, specifically through the Systems Analysis and Integration Campaign, trying to model some of these transition needs or model these transitions to HALEU field reactors, trying to estimate that HALEU needs, keeping in mind specifically current net zero carbon goals in 2050 within their modeling. A couple of limitations of some of the work that others have done. They all start with announced advanced reactor projects. So, starting specifically with the ARDP projects, the XC100 and the Natrium reactors, those getting built by the end of the decade, and then scaling up from there, kind of looking at what happens. And then they're also pretty prescriptive in their reactor deployments. They're based off of announced projects, or just only looking at a single deployment scheme. And as hopefully we'll get to with some of this work, that's always a limitation. There's how you deploy these reactors is really going, and which reactors you deploy is really going to affect your fuel cycle needs. They're also really just concerned with that HALEU mass, and what is that mass of enriched uranium that we need. They don't really consider other fuel cycle needs, such as that SWU capacity that you need or how much natural uranium you're going to need. So a little bit narrowed in their focus. So some of the work I'm trying to do, or that I did with my dissertation here, just in general, trying to understand changes to the US nuclear fuel cycle in order to commercially supply HALEU for these reactors. And then also understanding limitations of using downblended HEU in advanced reactors. So the objectives, the overarching goal that I had was exploring how the deployment of HALEU field reactors affects the US nuclear fuel cycle, and then also more specifically trying to quantify potential material requirements for the transition from light water reactors to advanced reactors in once through and recycling fuel cycles. So recycling being those closed fuel cycles. And then also understanding the impacts of fuel cycle parameters on the material requirements, and then potentially designing some optimized transition scenarios. And then this last one we won't get to today, but please feel free to read my dissertation if you're interested in it, trying to identify some of those limitations in using downblended HEU in the advanced reactors. So that part of it is more of on the neutronics and reactor physics side of modeling these downblended HEU compositions within these reactor designs and seeing how that changes different reactor parameters like your K effective. So getting into some of the transition analysis here, So looking at that second objective of quantifying material requirements, so I modeled the transition from current light water reactors to different advanced reactors. I use Cyclus, which is an agent-based open source fuel cycle simulator in order to model these transitions. If you want to know more about Cyclus, the website is fuelcycle.org. I do a lot of development work on that website, so please go check it out. And for this work, within the transitions, we can model the deployment and the decommissioning of different fuel cycle facilities, including the reactors. And then we can model the material transactions between these facilities. So how much feed uranium is going into our enrichment facility, and then how much enriched uranium is going into fuel fab, and then how much is going into our reactors. Ultimately, just trying to quantify that material requirement for these different fuel cycles.
Dr.
So
Bachmann?
looking at, yes.
Hi, we had a question if I think would fit in here. We had a question in terms of sources of where you could get the material. Any, EBR2 was mentioned and so forth, but how about, would the U.S. Navy be a source, or would NASA be a source? Do you have any thoughts on that, or have any information about that?
I have not seen any indication from the Department of Energy that they would be interested in downblending those stockpiles or those inventories. Really just the two that they've identified are the EBR2 spent fuel and then inventories at the Savannah River site. So that's all that they've identified publicly, at least.
Okay, all right, thank you.
Yep, great question. Okay, so looking at the transitions, we have a once-through fuel cycle, so going from our mine into a final repository. So we have the facilities for our light water reactors, and then we have our advanced reactor and the cooling pool for that. Modeling reactor deployments from 1965 out to 2090, beginning the transitions in 2025. So I took it as a pretty aggressive transition of, instead of the approach everyone else took of, okay, we start with these very specific reactor projects and scale up from there. I said, what if we scale up right now? Let me be optimistic in this work for a second. So that's what I did. The light water reactor commission dates and a lot of their data I obtained from the IAEA PRIS database. And the light water reactors are assumed to operate until their current license expires, based on what they have from the NRC right now. I also put in a caveat. I started all of this work, or I pulled this data in 2020. So neither of the Vogtle reactors are included in my modeling just because they were not operational at the time. And then I also do want to emphasize that I do assume that natural uranium is enriched to produce all of this fuel. So only looking at that HALEU production pathway. I didn't, for the transition analysis, consider the downblended HEU. And then the materials I looked at quantifying include the uranium mass. So how much of that HALEU would you need? Excuse me. That SPU capacity, the feed uranium, and then also looking at the back end of the fuel cycle, how much UNF or used nuclear fuel is produced that you would have to send to a repository for disposal. So there's 3 different advanced reactors that I considered for this work. There's the USNC MMR, which is a 5 megawatt electric microreactor. There's the X-Energy XC100, which is a 80 megawatt electric HTGR. And then the NuScale Voyager, which is a 77 megawatt electric light water SMR. And this one does not actually require HALEU. It requires a similar enrichment level to what our light water reactors need. But in my personal opinion, I saw this reactor design as very likely to be deployed alongside these HALEU-fueled reactors. And so I wanted to capture that within our modeling. And then based off of information in this chart, I was able to calculate how much enriched uranium needs to be in the core of each of these reactors based off of the thermal power, the cycle length, and then the burnup of the reactors as well. Looks like we have a question here. Will the delay in restarting the U.S. enrichment program in Portsmouth, Ohio for HALEU production delay the first SMRs? So I do believe that TerraPower has announced that their ARDP will start up a year or 2 later than they initially planned because of delays in HALEU availability. I'm not sure if there's been any other confirmed delays because of this, but that one definitely has been announced. Great question. Okay. So there's a lot of different ones through scenarios I modeled for this. The first one was just looking at the light water reactors. That way within the modeling, we can get a sense of what the light water reactors need, potentially compare that to some historic data. And then I considered various combinations of those 3 advanced reactors in either a no growth or 1% growth energy demand. So when you're developing these transition scenarios, how many reactors you need to deploy is a big question of that, because that's going to drive so many things about your fuel cycle. And so I determined the number of reactors that need to be built based off of a prescribed energy demand. And so when the transition starts in 2025 for a no growth energy demand, the advanced reactors need to be deployed in order to ensure that whatever power or electricity the light water reactors are producing in 2025 continues to be met all the way out through 2090, so the end of the simulation. And then for the 1% growth scenarios, I said that demand needs to increase 1% each year. So you have some amount of growth in that, and then you deploy the advanced reactors as you need in order to meet that energy demand. So for the purposes of time, I'm just going through the no growth energy demand results. So when I talk about how I determined how the advanced reactors need to be deployed, it's a modified greedy algorithm. So as this fictitious example shows, for scenario 7, which was deploying the MMR, the Voyager, and the XC100 together, in order to meet a fictitious demand of 530 megawatts electric, we're going to deploy 6 XC100s because they have the largest electric power output of those 3 reactors, and then we deploy 1 Voyager and then 1 MMR. The idea behind this being we want to minimize the number of reactors that are being deployed while also minimizing our oversupply of energy. So I calculated these deployment schedules in Python script, and then I provided that to Cyclist, and then Cyclist ran with it from there. So looking at just some of the reactor numbers, that just how many of these reactor designs do you need to deploy in each of these scenarios? And these results are totals, not reactor-specific numbers for each of the scenarios. So you see that this really just scales with the power output of each of the reactors. So scenario 2, because the MMR has such a low power output, just that 5 megawatts electric, you need a lot of these reactors, almost 18,000, versus when you're deploying just the XC100 or the XC100 and the Voyager in scenarios 3 and 6, you need quite a bit fewer, somewhere on the order of 1,100. So how many reactors you need is really just going to scale with the power output of the reactors, but then also with your power demand. So in the 1% cases, these numbers continuously grow with time. The next result we looked at is the amount of uranium mass. So how much of this HALEU do we need? And this is really a function of the reactor design. So in scenario 5, which is the MMR and the Voyager being deployed, we see we need the largest average mass of enriched uranium. And so for that scenario, because we have the MMR and the Voyager, not all of that is HALEU, right? The Voyager is less than 5% enrichment. And because of how that greedy algorithm works, with the Voyager having the larger power output between the MMR and the Voyager, we're mostly deploying Voyagers, which means that we don't really need that much HALEU in this scenario, actually, because most of the fuel is just going towards the Voyagers. And so we see that scenario 5 actually requires the least amount of HALEU of any of these scenarios. We also see scenario 2 requires the largest mass of HALEU, so just deploying the MMR. It's going to have the smallest power output. You need a lot of reactors, and so that kind of builds on itself in order to need a lot of HALEU. And then in scenario 3, which is deploying just the XC100, you need the smallest mass of enriched uranium. So yes, it's all HALEU, but overall for what you need, it's going to be less than the other scenarios. And this is, like I said, mostly a factor of the reactor designs, and largely just a factor of the burnup specifically. So the Voyager has a lower burnup than the MMR or the XC100, and so that drives a relative increase in the amount of enriched fuel that you need for that reactor compared with the other 2 designs. The next metric we looked at was the SWU capacity, and we saw that this, as I kind of previously talked about, it really is a function of the product mass and that product assay. So in scenario 2, which is just the MMRs, it requires the largest average SWU capacity, to produce the HALEU or produce all of the fuel. And that's because it has a medium level burnup of the 3 reactors, and then you also need an enrichment level that's at 19.75%. So you're right at the top of that HALEU category. So you need a relative increase in product assay or in product mass, and then an increase in product assay. So those 2 factors combine to really increase the SWU that you need to meet that scenario's demand. And then the other scenarios really need pretty comparable averages for the capacities that they need. And that's because in the XU100, we see you need less fuel than the Voyager, but you need fuel at a higher enrichment level. It's 15.5 versus a little over 4% is what I modeled here. And so you really see that increase in the product assay offset by the increase in the product mass. And so in this case, it actually kind of washes out between the two. And I do want to emphasize here that these enrichment capacity numbers are based off of assuming that you're always starting with natural uranium in order to produce the enriched uranium. So when you actually look at what this might look like for a facility you'll build, numbers may not quite be the same, and that's because of things like NRC category, facility categories of Cat 3 versus Cat 2. As well as cascade designs that you need in order to meet those product levels. So that was kind of the general trends that we saw within the 1-STIR scenarios, but always curious on what it looks like when you recycle your fuel. And so if we close that fuel cycle with these HALEU fueled reactors and these advanced reactors, wanted to look at how would that impact the material requirements. And then, we always talk about we should close our fuel cycle because it's going to save us on different resources. So how many does that really save?
Oh, Dr. Bachmann?
Yes.
I'm going to interrupt you just real quick. A question came in, and I think it fits right here. The question is, have you calculated the source terms of the spent fuel from the increased burnups with the HALEU? So I guess, do you know, like, which one would end up with the biggest source term at the end? Any way to characterize that? Or I'm not sure if that was part of your work.
Yeah, so that was not a part of this scope. That would be, really interesting future work to look more at some of the source terms and the isotopic vectors and how you might need to handle and treat some of these different use fuels on the back end for these 1-STIR fuel cycles. That's a really good question.
And then we have one more that just came in, is another question about if you change the reactor type, and again, this is maybe a little bit outside the work you did, but if you had a natrium reactor at 345 megawatts, would that, I don't know whether that ever entered into your work, or you can comment on anything like that. So there's a reactor at 345 megawatts,
Yes, that's a really good question because it does have a larger power output than the reactors that I looked at here. And unfortunately, I really did want to look at the natrium, being an ARDP reactor. I felt like that would be really pertinent to include in this work. But unfortunately, when I started, they didn't quite have enough information that was publicly available in order for me to include that in my modeling. So yes, it has a larger power output. So you need to deploy fewer reactors, but off the top of my head, I'm not sure what enrichment level that they need for their fuel. And being an SFR, they tend to be larger cores. So how those things kind of offset each other. I don't have the exact numbers to really kind of even guesstimate on that, but that was something I was hoping to look at within this work and wasn't quite able to include, but it's a really good question.
Okay, great. So, and just as a timekeeper, we're right about at the half hour.
Okay, perfect. So I'll go through these next little bits kind of quick. So these next couple of slides, I do encourage you to read this in my dissertation. Hopefully we can get a paper out about this next set of slides real soon. But basically for this, in order to more accurately model the closed fuel cycles for this work, I developed a new reactor model within Cyclist that couples with OpenMC and their standalone depletion solver. So that way you can do dynamic depletion while you're doing these fuel cycle models and have more accurate spent fuel compositions, which means you can have more accurate numbers for how much of material can be pulled out and reprocessed, as well as eventually potentially getting more accurate spent fuel source terms. So I'll kind of skip through different things on this, but this kind of outlines the theory of what I did. It's called OpenM Cyclist. It is publicly available on GitHub if you want to check it out. And so it's just and then this is kind of how I benchmark this against the method in Cyclist that I was using for the once-through scenarios. And so comparisons showing, the spent fuel numbers are different, but we kind of expect them to be different because of the differences in the methodology. And then everything else matched up as we expected it to. So again, if you're interested in that, I encourage you to read that in my dissertation. So then I use that new reactor model within Cyclist in order to model these recycle scenarios. And so I looked at basically 3 iterations of a closed fuel cycle, considering that no growth and that 1% growth energy demand. So I looked at the 3 advanced reactors being deployed in what we call limited recycle schemes. So the fuel goes into the reactor as uranium-based fuel, or like in light water reactor world terms, the UOX fuel. We take it out, we reprocess it, turn it into a more plutonium-based fuel or a MOX fuel, put that back into the reactor, and then that MOX fuel just gets disposed of. We don't continuously put the MOX back through. So we still limit the number of times that the material goes through the core, but it does go back through more than once. And so I did a scenario of if we can reprocess all of the advanced reactor fuel, and then also a scenario of if we can only reprocess the fuel from the Voyager reactor, because the XU100 and the MMR both utilize TRISO fuel kernels, and TRISO fuel is very hard to reprocess. So I wanted to kind of capture that within my modeling of how much that affects the results. And then I also wanted to look at what happens if we deploy a fast reactor meant for continuous recycling schemes. So fuel really just keeps going through the core, and then separated out and then back through the core, and so on and so forth. And so ideally, you're only really disposing of your fission products in this scenario. So once again, going to just go through some of the results on the no growth energy demand result scenarios. So when we talk about that limited refuel cycle, this is kind of what I was saying of, material kind of comes out, goes into separations, put it back in. Once it's gone through the reactor that second time, you just dispose of it. And then for this modeling, I said that separation step was only going to remove plutonium to emulate and model an aqueous reprocessing method, which is what we'd likely use within this fuel cycle. And then same deployment scheme as scenario 7 or 13, depending on that energy demand. And then model the XU100 and the Voyager with OpenM Cyclists. The separations start in 2020, so you have about 5 years in order to get separated material that you can then use for your advanced reactors. Excuse me. And then, like I said, I varied if the TRISO UNF was going to be reprocessed because of current technical limitations on reprocessing TRISO fuel. And then when I talk about the continuous recycling scheme, the fuel really just goes through this loop an unlimited number of times, with fission products continuously being taken out in that separation step. That separation step is also going to remove your uranium, neptunium, plutonium, and americium, trying to model more of an electrochemical reprocessing system, which is what we'd more likely use in this type of fuel cycle with a fast reactor. And then use that greedy deployment scheme to figure out how many of the fast reactors we need to deploy for this scenario. So for the fast reactor that I modeled here, it's largely based off of the GE Hitachi Prism reactor, so sodium-cooled fast reactor with a metallic fuel. So it has that 311 megawatts electric with a burnup of 87.5 megawatt days per kilogram. So this is about as close as I got to modeling that natrium reactor, but again, natrium's a little bit different. And then I also really only considered the fast reactor for that continuous reprocessing scheme didn't look at it for the once through scenario. So in retrospect, I could go back, apply the fast reactor to the once through modeling scheme and see how that compares to get at least a ballpark, I think, of what the natrium would look like. So when we look at just the amount of actinide material that we get out of our advanced reactor fuels, so kind of looking at when we have the limited reprocessing and then also when we have all three of them, that recycling scheme is going to dictate the amount of separated material that you have. For scenario 16, that's that continuous reprocessing. So we're taking out the uranium and multiple transuranics. And so really just by taking out the uranium from that separated material, that's the primary factor that drives the amount of separated actinide material that we have, because most of your spent fuel is going to be uranium still. Versus for the other scenarios, we're really just pulling out the plutonium. And so that's really going to limit how much of that separated material you can get. And then in scenario 15, which was that limited recycling, but not reprocessing the TRISO fuel, we see that eventually it goes nearly to zero because you're just not deploying very many Voyager reactors. And that's the only fuel after a certain point that you can reprocess. So that also very much limits the amount of separated material that you have in your scenario. We also see that recycling decreases your HALEU needs, which is more or less what we expected to see out of this. In scenario 15, which is that limited recycling but not reprocessing the TRISO fuel, you're going to need more enriched uranium than the other scenarios because it has the least amount of material that you're getting out of your used fuel. So you need to compensate more with more fresh HALEU. And then in scenario 16, which is that continuous reprocessing with the fast reactor, at some point, you don't really need any more enriched uranium because you have so much of your plutonium-based fuel that you can put back into your reactor because you are taking out so much of material from your spent fuel. So looking at the transition analysis here, we really saw that the advanced reactors that you deploy are going to drive your material requirements for each of your scenarios. If you close that fuel cycle, whether it's limited or reprocessing, you're going to decrease your HALEU needs, but how much you decrease it by is going to be driven by the reprocessing scheme that you use and what material you are reprocessing. And then you have a decrease in your HALEU needs driven by material that's available from your reprocessing and what you separate out from your UNF. So something that I noticed with all of this is these scenarios really look at large changes within your transition. So, just different reactor types that you're deploying, different fuel cycle schemes in general. But, when we talk about fuel cycles, there's a lot of little levers that you can push and pull and dials that you can mess with just a little bit. And so, looking at some of those smaller changes really drove the next part of this work, which we'll probably just get to the sensitivity analysis, not so much the optimization here. So with sensitivity analysis, trying to look at how some of those smaller parameters within the fuel cycle transition might affect our results. So for this, I coupled Cyclist with Dakota, which is an open source code from Sandia National Lab that is meant for sensitivity analysis, optimization, and uncertainty quantification. So I looked at parameters such as your transition start time. So I said, let me be optimistic, and we're going to get full-scale fleet reactors up in 2025. All right, yeah, you caught me on that one. So I, looked at what happens if we push it back to 2040, in various increments between 2025 and 2040. Also, what happens if, some of our light water reactors are able to operate for 80 years because they can get license extensions? How would that impact these results? What if we're deploying all three of these different advanced reactor designs, but we say that a certain amount has to be met through this one design instead of using that greedy algorithm? And then also, so the XC100 and the MMR currently are designed to get burnups that are higher than NRC regulations allow for. So I kind of wanted to play around with what happens if they maybe can't quite get that high burnup that they're supposed to, because there's a lag in the regulations or something happens. So just kind of varying some of these smaller parameters that are within our fuel cycle. And then the output metrics I looked at, very similar to the transition analysis. So how much uranium mass that you need, how much of that HALEU do you need, how much SWU capacity that do you need to produce all of the enriched uranium, the SWU capacity just to produce the HALEU, the feed uranium to produce the HALEU, and then also that UNF mass. So I vary the parameters individually as well as in multiple combinations. So we'll go through just some of these results. And then when we talk about the build shares for the reactors, specifying the build share for a single reactor, and then you deploy the others using that greedy algorithm. So first result I want to look at is what happens when you vary the MMR build share. So if we say 0 to 50% of the energy demand has to come from MMRs, what does that do for each of these material requirements? And all of the materials requirements increase, and the enrichment related metrics are going to increase the most. So you see up here the HALEU SWU, the total SWU, and that HALEU feed increase more than your UNF mass or your fuel mass. And that's because it's that compounding effect of increasing your product mass and increasing your product assay with the MMR relative to the other two reactors. Excuse me. And like I said, the results are a function of the number of reactors of each reactor that are deployed. So, we see that as we increase the build share of the MMRs, we're increasing how many of those are deployed. We're decreasing the number of XE100s, but the number of Voyagers is actually pretty constant. And so that's because I'm still have that greedy algorithm within my deployment scheme here. And so it becomes a teeter-totter between the MMRs and the XE100s. So the MMRs need more fuel, higher product assay than the XE100s, and so that really drives all the material increases that we see. Next, when we look at varying the XE100 burnup as well as that MMR build share, we see some pretty interesting results here. So because we're varying that MMR build share, we still have this teeter-totter effect between the XE100 and the MMR and the materials that they each need. But when you also affect the XE100 buildup, we see that it's a non-uniform change across this design space. So when we have the smaller XE100 burnups, so looking at this side, having that lower burnup in the XE100 actually means that the MMR is going to need less fuel than what we see than what the XE100 is going to need. So that's why when we're at the low burnups, we see that increasing that MMR build share actually decreases the HALEU mass that we need. But then when we get the XE100 up to those higher burnups, closer to that 168 that it's designed for, it's going to need less fuel than the MMR needs. And so that's why we see it increase across the MMR build share space when we're at these higher burnups. And then also I wanted to look at what happens when we vary a lot of these parameters at once. And so what this chart here is something called a Sobel indices. So it's a value between 0 and 1 to kind of explain, to represent the amount of variance that you see in your output parameters. So in this case, the fuel, the HALEU, the SWU, et cetera, how much of the change that you see in that output space is because of changes in this one variable. And so we see that when we're changing the MMR share, the XE100 burnup is that driving factor for basically all the changes in each of these variables. And so that really highlights the importance of the burnup and the design characteristics of these reactors that you're deploying in each of these transition scenarios. So for each of these, it's above 0.5, it's even up to 0.9. So this is a really, really impactful parameter on your material requirements. So that burnup's really important. So I'll go ahead and skip this part, get to some conclusions here, so we can kind of wrap up the night. So my work for my dissertation investigated the impacts of deploying HALEU-fueled reactors on the U.S. nuclear fuel cycle. We saw that from the transition analysis, the material requirements that you need for your transition are governed by the design characteristics of the reactors that you deploy. When we close the fuel cycle, we're going to decrease those material needs, but that decrease is going to be governed by the recycling scheme and then the material that's available for reprocessing, such as if you're reprocessing all of the fuel from the advanced reactors or just that non-TRISO fuel. The sensitivity analysis that I looked at highlighted how the advanced reactor characteristics affect those material requirements and really how important that XE100 burnup is within these scenarios that I modeled. when I talked about the optimization part, you know, we're able to do that, but could be improved a little more. Encourage you to look at my dissertation for more information on that. And then, spoiler alert, the impurities from downblending the HEU, at least in how I modeled these reactors, it does affect the parameters a little bit, but it won't necessarily prevent key design parameters from being met. Like, you can still stay at least critical throughout the entire intended lifetime of the reactor or cycle time of the reactor. You're not necessarily going to have positive reactivity coefficients, things like that. But you do see changes. It just, you know, won't prevent your reactor from being deployed with this fuel. So this is kind of just dissertation stuff of providing, you know, really detailing what I did to expand the science. Limitations in future work. So the transition analysis I here really provided what I call a macroscopic view of material needs. I looked at things on a pretty aggregate level, but you know, for future work, you can really dig into some of those finer details of, okay, what's needed exactly for each reactor, what's needed exactly for each fuel type. You know, if you break up your enrichment facilities into the category 3 and category 2 facilities, what would each one look like? What would your cascades look like? Just getting more detailed and more into the weeds of this fuel cycle specifically. Yeah, so just kind of going into things like that. And then also things like accounting for processing time, you know, did some academic hand waving and said, okay, we have everything when we need to, but, you know, it takes sometimes a good couple of years in order to do your entire fuel cycle in order to have material ready for your reactor. So accounting for that and your lead time and when some of these facilities might need to be up in order to make sure we have the material for our reactors. And then also looking at things like non-fuel materials like reactor grade graphite. The XC100 and the MMR being trisofuels, they have a lot of graphite in them. And so, you know, considering that supply chain as well. Providing some acknowledgements. I was fortunate enough to have a UNLP, or you might know it as NEUP, the Nuclear Energy University Program's graduate fellowship. I was also supported under a surge fellowship from the Granger College of Engineering at the University of Illinois. Huge thank you to my committee members. Thank you to the Advanced Reactor and Fuel Cycle group members, so all the fellow students that I had supporting me in grad school. And then also the reactor and fuel cycle analysis members. So that's my current group at Argonne. I also did some of this graduate work with them, specifically Drs. Bofang and Scott Richards, the cyclists and OpenMC communities. They were super supportive in answering all of my questions, which, yes, there were a lot. And then also my significant other, Kyle, and little R, my rabbit, were great supports as well. Provide some references here. And this is little r, this is my rabbit. The R stands for Röntgen, yes, as in the physicist that discovered X-rays, because I don't know, I just needed a pet with a really nerdy name. So thank you all so much.
Dr. Bachmann, thank you. We have a question in the chat. I don't know if you can see that. Or the Q&A, I'm sorry.
Yeah, so beyond genetic algorithm optimization, what other methods would you recommend in future analysis? So at least within Dakota, which is the tool I coupled cycles with also for the optimization, there's a lot of different methods. They have in their user's manual some recommendations based off of the type of problems that you have, the different methods that might be applicable to your problem. Unfortunately, nothing specific is coming to mind. It's been a little bit since I've had to read through that, but for this work, I did choose genetic algorithms because it's something I'd pretty commonly seen used for fuel cycle optimization, and you know, they're available in Dakota. They just, the way they're programmed in Dakota, they're not great with linear constraints, which was something I applied in this work. So that's why I kind of mentioned, you know, might want to look into other algorithms.
Okay. Then let's see. Oh, and here we have another question, if you can see that.
So I believe the most recent novel fuel production attempt in the U.S. was Savannah River's MOX, also stockpile downblending. Do you believe the regulatory and financial issues that led to SRS's MOX supply chain failure challenge the timeline assumptions of the cyclist analysis? Oh, that's a big question. So I will say actually, oh gosh, what company is it? I think it is USNC does have a fuel fabrication facility in Oak Ridge, Tennessee that is based on criticality limits about as big of a facility that they could have for the fuel that they're producing for their reactor. So Savannah River is not necessarily the only data point we have for this. You know, my big assumption being that we would deploy basically a fleet of advanced reactors in 2025, I knew was maybe on the less realistic side. But I did see within my transition analysis, as we push that start date back to like closer to like 2040, it compared to some of the other parameters I explored, it actually really didn't affect the materials that you need. Which was really interesting. I think it was mostly just because of how it changes which reactors are deployed, because you kind of need to meet like a larger initial jump, excuse me, in energy wall. So it changes which reactors and how many of them are deployed. But yeah, so, and I know also X Energy through, I think, Triso X is that arm of their company. They're working on really getting fuel fabrication up and running for their reactors as well. And so, you know, people are looking at the HALEU problem, but they are also looking at that fuel fabrication problem to, you know, minimize some of these delays as much as they can.
You know, and one question I had was just, well, two really. One is, you know, I've been away from this for a long time, is, you know, there was always a constant battle between the SWUs and the material in terms of cost and availability and things like that. So I don't know if there's anything about costs that entered your work that you could comment on.
Yeah, that was outside the scope of my work.
And that's
Yeah,
fine.
that data is kind of hard to come by.
Yeah,
sometimes.
yeah. And then I guess one observation I wondered if you could either confirm or deny or refute is it seemed based on the work that you did that the microreactor seems more like a niche, and I think it was originally designed to be like a remote access, you know, thing, not like you would not have one in every neighborhood kind of thing. And you know, but you have looked at this from the fuel cycle in much more detail. You know, any comment about, okay, if someone came to the Congress and said, hey, we should put one of these in every neighborhood or a large building, what, I mean, it seemed like that would be not good.
Yeah, I mean, every reactor design is going to have its own advantages and disadvantages, and you know, most of them are meant for more specific energy markets, such as I know some of the microreactors are meant for like more remote communities or potentially military bases and things like that. So they do meet those needs quite well. From a fuel cycle perspective, they're maybe not the best to be deploying, you know, trying to meet 100 gigawatt energy demand, which is about what I had in these scenarios. So yeah, from that perspective, not the best, but they do a good job of meeting their intended purposes.
Right. And we'll call this one the last one question, if you can see that in the Q&A.
Thoughts on infrastructure changes beyond the fuel fabrication facility to handle and store HALEU fuel? So a really big thing that people have been looking at are transportation casks. And that's not necessarily for the spent fuel or what comes out of the reactor. That's more of even just to transport enriched uranium to a fuel fabrication facility, right? When you're at those higher enrichment levels, you have different criticality concerns, criticality safety concerns. And so making sure that, you know, criticality safety is paramount, is, you know, being met and being upheld. And so looking at, you know, what canisters can we use? Can we just modify what we have now? What if we can't, then, you know, what do we need to build? What do we need to license for that? So I've seen quite a few papers and quite a few reports on just how can we transport this higher enriched uranium.
Okay, very good. And with that, let's see. I'm gonna come back on. So again, this is Eric Jepson. Thank you very much to our speaker, Dr. Bachmann. Very entertaining talk, and a lot to chew on there, and a lot more to go. It's like you know, I'd have to take a break and come back for seconds. This is like Thanksgiving dinner on steroids. So thank you very much again. We're definitely going to have you back as you progress in your work. And thank you also to all the folks who showed up on the Thursday night before Good Friday. Stay tuned for more to come. And again, the slides, link to the dissertation is available, and the recording will be made available also. And with that, I think we'll ring off. Thanks also, of course, to Dan Goldberg at ANS Nashville for doing a lot of logistics work behind the scenes, which you don't see, which makes this run very, very smoothly, much more smoothly than if it was in my hands alone. So, and Alan Metzger, who was on the sidelines looking at questions and fielding questions. So with that, we'll ring off. Have a good evening and end of